Welcome to another podcast. In this episode, we're going to be taking a look at how to derive the spring mass equation. This is an equation which we're going to use in one form or another throughout most of the rest of the semester. So it'll do you a lot of good to familiarize yourself with the terminology and equations involved. We start with sort of a simple picture here. Let me just kind of explain what is going on in this picture. We have a spring which is attached to a mass. And also attached to this mass is a dampener, which we usually call a dashpot. And each of these has with it a constant that sort of associates it with how much damping or how much restorative force the spring has. So when we talk about the different pieces of this puzzle, K is the spring constant. The spring constant comes from an experimentally verified law called Hooke's law, and we'll talk more about that here in a little bit. The other piece to this puzzle is the value C, which we'll just call a damping constant for now. We're going to let K and C, so we've got M is the mass of the object. And then I want F to be an external force. Now, the idea is there is some special value of X where at that value or at that level, we're in equilibrium. So I'm just going to say that right here is the value of X where the spring is just hanging freely. It's neither oscillating up nor down. And it's at this point X naught that we achieve what we would call equilibrium. And so just as we had with the mixing models earlier in the course, with spring mass models, there is sort of a balance law that plays into our discussion here of what's going on. And it turns out that the balance law for this particular equation is a more famous law, and that is Newton's second law. So Newton's second law states that the forces acting on an object balance with the mass of the object times its acceleration. And so what we need to uncover is what are all of the forces, in other words, what are the total forces acting on the mass M. Well, let's start with the maybe one of the simplest forces to explain, and that is the restorative force, which I'll write R as a function of X. So this is the restoring force. This is the force inherent in the spring to pull it back towards equilibrium. So if I think about, moving the mass, it's going to oscillate back and forth, and one of the sort of this tug of war between gravity pushing it down and the spring pulling it back up. And so this restoring force is the force due to the spring. We'll talk about exactly what that force looks like here in a second. We also have the force due to gravity pushing down on the object. We have the force exerted through damping. So that's what this term is. This is the damping force. It's proportional to the velocity, and we'll talk about that here in a second. So it depends on the velocity. X is the displacement. So the restoring force depends on the displacement. The further you push it away from equilibrium, the harder it's trying to pull back. The velocity, the damping force, here we think of it being proportional to velocity in the sense that if you've ever tried to slam shut a screen door, screen doors often have dashpots on them, and the harder you try to press the screen door closed, the more it resists that. And so the damping there is proportional to the velocity at which you're trying to close the door or close the spring or act on the spring. And then finally, we have the external force, which we'll call F of X at this point. So what do these forces look like? Well, the restoring force is directly proportional to and in opposite direction of the force due to gravity. So if we look at the picture, the spring constant K, this is Hooke's law. So Hooke's law tells us that the restoring force is directly proportional to the displacement. and it acts in opposition of the force due to gravity. So force due to gravity is pushing this in the positive direction. The restoring force is pulling it back in the negative direction, at least in this case. So we're orienting this so that the positive direction is pointing down. Let's see, the mass times gravity we'll leave alone for now. That's the force due to gravity. If we look at the damping coefficient, this is just the damping law, so it's directly proportional to velocity. So we'll use some damping constant c here, which is the constant that we have in the picture. And then for now we'll leave the external force all by itself. So while this is good, it's not a complete enough picture because I haven't factored in what happens at equilibrium. And so when x equals x naught, in other words, when we're in this happy equilibrium phase, then the tug-of-war between the spring wanting to restore it and gravity pushing down on it is equal. What that means is the restoring force at the point x naught equals the force due to gravity. We know the restoring force is minus k times the x value. And so what we have discovered here is a way to write, or a way to replace mg with negative kx naught in this case. Since those two are equal to each other and they pull in opposite directions. So really it should be like this. And what we have is kx naught equals mg. So I can update my graph here, or my equation here, with kx naught minus c times v plus f at x. And if I get ready now to write an equation, let's look at the left side of the equation as m times a, but a is the acceleration of the object, and so that is the second derivative of the displacement, is equal to minus k times, I've got x minus x naught, so if I take and combine these two terms, minus c times the velocity is x prime, and then f of x is the external force. So sort of putting everything together here, I have kx minus x naught plus c times x prime equal f of x. And this is starting to look better. But the final step is I want to make a variable substitution. I want to let y replace the variable x minus x naught. And the reason I want to do that is y is going to track displacement, but it's a specific displacement. It's the displacement from equilibrium. So this is going to tell me how far away from equilibrium I get. When I make that change of variables, x double prime is y double prime. Cx prime is cy prime. And I've got k, x minus x naught is y, equals f of x. And so if we stop and stare at this final answer for a second, this is a second order linear inhomogeneous, as long as f of x is non-zero. It's an inhomogeneous equation with constant coefficients, which means that all of the characteristic equation method stuff that we've talked about in previous videos carries over to solving this particular model. So knowing what the characteristic roots are, knowing whether they are real and repeated, real and distinct, or complex, is going to give us additional insight into this particular equation. And so the boxed equation down here at the end is something that you should definitely commit to memory. It's the way to relate the mass, the damping, and the spring constant of a spring to the displacement y, subject to an external force F. And so putting all of these sort of pieces together, we've now derived the spring mass equation, and it's not the last time that we're going to use it. We're going to use it in several other contexts all throughout the rest of the semester, starting with the very next video, where we're going to take a look at simple harmonic motion. All right, thank you for watching.